at Harvard, and I will be speaking about deconfined critical point in a random Heisenberg magnet. So my original title of the talk was Phases of a Random TJ Model. I've just modified the title of my talk, and the reference can be found here. So this work was done in collaboration with Chenyuan, Grisha, Antoine from Flatiron, and Subir Sachdev here guiding us. So basically, what I'm interested in is the cuprate phenomenology as a motivation. So in the recent experiments, it has been found that things drastically change as you do hole doping in cuprate compounds, and after a certain critical value of the hole doping, there are drastic phenomena happening. So for example, on the left plot, what you see is an electronic heat capacity as a function of hole doping, and you see that it diverges at some critical doping value. In the right plot, basically this is some Hall measurement, and you see the carrier density in this experiment as a function of hole doping again. And you see that at low hole doping, the carrier density is basically P, whereas it suddenly jumps at some critical value of the doping PC, and it becomes 1 plus P. So, and there are some other experimental evidence from photoemission experiments, let's say, that suggests that things are really changing at some critical value of doping. So does this mean that there is a possible quantum critical point in this cuprate phase diagram underneath this superconducting dome? And to explore that this could be a possibility, we basically consider a model, and I would demonstrate that we in fact find an evidence that there could be a quantum critical point here as a function of doping. So the model that we consider is basically a random TJ model. So here the first term is basically the hopping between electrons, which is the amplitude is Tij. Then there is the Heisenberg exchange term, where the amplitude is the exchange interaction is Jij, and then there is chemical potential mu. So this is the TJ model, basically comes from the Hubbard model, and now you impose no double occupancy, and we are considering hole doping. One thing to note is that this Tij and Jij, these are random numbers now, instead of constants in the usual TJ model, and they are random numbers such that the mean is 0 and the mean square is like t square and j square. So this model, basically without the t term, was initially solved by Subir Sachdev and his student, which now goes with the famous SY model, and there they found interesting solutions in the large M limit or spin liquid. And in fact, the model with t was also considered by Oliver Pacolet and Antoine Georges. So you will see the new things that we have been doing now by adding these terms. So basically in this model there are 3 states. Since we have excluded double occupancy on every side, you have either a hole on state, which is basically an empty site, or you could have a spin up or spin down state. So these are the spin-ons. And now one can consider a SU12 superalgebra, meaning that you now have a bosonic holon and a fermionic spin-on. And in terms of this, you can write down your electron operator and your spin operators in terms of this fractionalized degrees of freedom, F and B. And this constraint on the right-hand side is nothing but the constraint of your Hilbert space, that there cannot be double occupancy on every side. Just for completeness, I just want to mention that you can also equivalently describe this in terms of a bosonic spin-on and a fermionic holon. This is just an alternate formulation, and things will basically be the same. Okay, so this is our model. Now, since these Tij, Jij are random numbers, we basically do the replica trick, do disorder averaging, and we find an effective single site action. So this is in a spirit of what also people do in DMFT. You find some effective single site action. Things have simplified a bit because now we got rid of some random numbers, and now we have an on-site problem. But still, it's a formidable problem because what you see here, there are these fields R and Q, which basically these are related to some correlators of electron and spin operators. And the thing that makes it complicated is that you have to solve these fields R and Q self-consistently. So it's not very easy to solve this analytically or even numerically. It's a very challenging problem. So although we have simplified it a lot, still it's quite a formidable problem. Now, the interesting thing is that since we are interested in a critical point or critical phenomena, let's assume that this R and Q have some power law behavior, like Q goes as 1 over tau to the power d minus 1, and R goes as 1 over tau to the power r plus 1. So this R and D are some numbers basically. And if we assume this, then things actually simplify. What you can do is we can map our original problem onto an impurity problem now, where basically we have introduced some bosonic and fermionic baths. So here gamma 0 is the coupling of the spin operator. So this F sigma F, if you recall, this is nothing but our spin operator. It's coupled to a bosonic bath. And F dagger B is the electron operator. And this is now coupled to a fermionic bath psi. So this is basically like a super Kondo problem where your original degrees of freedom, the electron and spin, are now coupled to some bulk baths, bosonic and fermionic. And this S0 is a mass term in this case, and lambda is basically related to your putting the constraint of the Hilbert space. And here we set lambda to infinity. There are technical reasons using which you can justify that this actually gives you the correct constraint. Okay, so once we have formulated now our original problem into this impurity problem, we can do renormalization group now in terms of the small parameters epsilon and r bar. So epsilon is related to this exponent where the parameter d comes, and r bar is this exponent, this value r, which comes in this exponent. Now we can use the usual tricks of renormalization group, and what we find is that in the G and gamma, so G and gamma are basically the couplings of the fermionic and bosonic bath coupling to the spin and electron operators. And what we find is that in the RG flow of this G and gamma plane, there is a stable non-trivial fixed point. And these are the beta functions that we can evaluate to two-loop order. So this is the point that we are interested in. So this is the non-trivial fixed point, which is stable, and this could potentially be our quantum critical point, as I will show it to you. But what is remarkable about this non-trivial fixed point is that at this particular non-trivial fixed point, you can exactly calculate the anomalous dimension of the electron and spin operators to all orders in this epsilon and r bar. So this is kind of an exact result, basically, which tells us that the electron correlator has the behavior 1 over tau power 2 bar, and the spin correlator has the behavior 1 over tau power epsilon. But recall that we have to satisfy this self-consistency condition to close the loop and solve our problem. So we are not done yet. And now we basically close the loop by demanding that the self-consistency is satisfied. So basically demanding that these exponents match with the exponents that we started with, d minus 1 and r plus 1. And it's a very simple algebra that basically tells you that epsilon and 2r bar have to be 1 exactly. And remarkably, what this means is that the electron correlator behaves as 1 over tau, which is not very surprising. But what is interesting is that the spin correlator is 1 over tau. So just to refresh, the Fermi-liquid behavior for the spin correlator is 1 over tau square, whereas what we find here is a 1 over tau behavior. So indeed, it means this is not a Fermi-liquid. And moreover, it means that actually the fractionalized degrees of freedom are important, which basically gives you this 1 over tau behavior. Okay, so this is the feature that we find at this quantum critical point, and this is in fact a deconfined critical point because there are fractionalized degrees of freedom f and b, only using which you would have such a behavior for the spin correlator. So now we also can ask the question: does this deconfined critical point actually mimics what I suggested in the beginning? And in fact, it does. So if you think about it, this S parameter in the impurity Hamiltonian was like a mass term, and the S parameter is a relevant operator in this RG. You can work out the beta function for this, and one can show that actually this is the parameter that drives the phase transition. This is the relevant direction. So for large S, it's basically like large doping, whereas small s, or negative s actually, it means it's small doping. And you can now understand the entire phase diagram qualitatively in terms of this. So basically at PC, this is where we solved our theory and found this deconfined critical point where we had the holon and spin-on states which are nearly degenerate, and the spin correlator was 1 over tau. Now, as I increase the doping, basically the bosonic holon will condense, and you will have the usual Fermi-liquid behavior with the particle carrier density 1 plus p, whereas if I go on the other side, I can condense the spin-ons by using the SU21 algebra, and I get the metallic spin glass phase. And here the spin correlator is actually a constant. So this is the phase diagram, and this is the deconfined critical point that we found. And interestingly, at the 0th order, we can also find the value of this critical doping, and it's 1/3. Yeah, so basically this is the phase diagram, and to summarize, what we have done is consider this microscopic model, a random TJ model, where we find a deconfined critical point as a function of doping. And we can also connect this to a large, by introducing a Hubbard model, and this is interesting numerical and analytical work that Grisha did, and people at Flatiron have done this numerically. So numerically, they find spin-spin correlator as 1/tau as a function of 1/u for this metal-insulator transition. And one can speculate a phase diagram where you have 1/u on the y-axis and doping on the x-axis. So what I showed you was this particular point at very large u, basically, and then doping the system. And here there is another point which has been solved, which is a metal-insulator transition, where again you find a 1/tau behavior for the spin correlator. And one can speculate that there is probably a phase diagram where this is the critical line which separates basically the metallic spin glass and the disordered Fermi liquid. And moreover, this was just one part, the RG that I showed you. This is also complemented by large M saddle point analysis for the same model, and there also we could show that this is indeed a deconfined critical point. And there are many interesting aspects that one can think about. Thank you. Yeah.
Do you know what universality class that critical point is?
Sorry?
Do you know what universality class that critical point is?
What universality class? So that's
Is it meaningful?
Of course, it's a meaningful question. So in this particular case, I don't have the answer at the top of my head, but this is basically the deconfined criticality. So it's in the universality class of all these deconfined critical points. I guess that's not a wrong answer.
Well, it's an infinite range model, so you can't. Universality class varies according to dimension, so this is like infinite dimension. So I would say it's SYK universality.
SYK universality, yeah.
Just actually, should I think of it as infinite dimension or 0 dimension?
Or both.
No, it's infinitely connected, and yeah, point-like.
Great. So I missed the fact that there were long-range interactions. What are,
No, there are, I mean, it's not really, yeah, there are long range, but basically the interaction J or T is basically all-to-all and random. So all the points, basically there are n points and they are all connected to each other.
Oh, I see.
Yeah.
And it doesn't decay with distance at all. It's the same.
No, it's just some random number, Jij or Tij. Yeah.
By infinite, what actually mean like the system size?
Sorry?
By infinite?
Yeah, so we, in the end, we will take the limit that the number of points or number of sites are infinite. Yes, we take this limit. But that has that does not mean the dimension in any sense, right? I mean, this is the thermodynamic limit that we send n to infinity.